We will now do a new chapter where we will study various types of convergence. So the first section in this is Egorov's theorem. So theorem Egorov. So let x s mu be a finite measure space. That means mu of x is finite. Let Fn be a sequence of real valued measurable functions converging almost everywhere to a real valued measurable function f. So we saw in the exercises that if mu is not complete, then it's not necessary that f be measurable. So we are now specifying that the limit is also a measurable function. Then given any epsilon positive, there exists a measurable set f contained in X such that mu of f is less than epsilon and Fn converges to f uniformly on f complement. So we have convergence almost everywhere. Then this convergence is practically like uniform convergence, except it may not everywhere. So then it's not, obviously you can't have an arbitrary convergent sequence to be uniformly convergent. But what's the remarkable thing is, if you are in a finite measure space, then you can choose as small a set, a set with as small a measure as you like, such that on the complement this sequence is in fact uniformly convergent. So proof. So let E belong to the sigma algebra such that mu E equal to 0 and Fn converges to f uniform, on E complement. So you set y equal to E complement. So then given nm positive integers, you define enm equals intersection I equals n to infinity x and y such that mod fix minus f of x is less than 1 by n. Okay. So clearly you have E1m. If m is fixed, you are taking intersection from n to infinity. So as you go up, n increases, then you have an increasing sequence. Now x belongs to y. If x belongs to y, then you know that fnx converges to f of x. Okay. And so for any m, there exists a capital N such that for all I greater or equal to n, we have mod fix minus f of x is less than 1 by m. That means x belongs to EINM. So this implies that y equals union n equal to 1 to infinity ENM for every m. So mu y is the same as mu x. because it's y equals y union e is the whole of x, and e as measure 0, so mu y equals mu x, and this is less than plus infinity. Now therefore you have mu y, since it's the increasing limit of sets, you have limit n tending to infinity e n m mu of e n m, and because of the finiteness you have implies there exists n0 of m such in n such that mu of y minus e n naught m which is mu y minus mu e of n naught m, and this can be made as small as you like because of this limit here, and I am going to choose epsilon by 2 power n. Now you said G equals union m equals 1 to infinity e n naught m y minus e n naught m. Then G measurable, and you have mu G is less than or equal to the measures of these sets, which is less than epsilon by sigma epsilon by 2 power m, and that's equal to epsilon. Now you set F equals U union G, so that mu of F equals mu of G, which is less than epsilon. And what is F complement? F complement is precisely intersection m equals 1 to infinity e n naught m. So let eta be greater than 0, choose m such that 1 by m is less than eta. So now if x belongs to F complement, then for all n greater or equal to n naught m, so x is in F complement, and therefore x belongs to E n naught m which is less than E n m for all n greater or equal to n naught m. So if x belongs to F complement, for all n greater or equal to n naught m, you have mod fnx minus fx is less than 1 by m, which is less than eta. So this is true for all x in F complement, and therefore you have that fn goes to F uniformly on F complement. And that and measure of F is of course less than epsilon, and therefore that completes the proof of Egorov's theorem. So example, not true for infinite measure spaces. So you let us take x equal to the natural numbers, s equals the power set of x, and mu equals counting measure. So what do you mean by saying mu f less than epsilon? So if epsilon is less than 1, this implies that mu f equal to 0, which implies that f equals the empty set. Therefore, uniform convergence on F complement is the same as saying uniform convergence on N. So now you look at Fn. Fn equal to chi of 1, 2 up to n. Then Fn converges to F, which is identically equal to 1. Sorry. Yeah. But this convergence is not uniform. So the Egorov's theorem fails in case of infinite measures. So inspired by this Egorov's theorem, we make the following definition. Excess mu measure space Fn real valued measurable functions defined on X. We say that the sequence converges almost uniformly. Here you must, this almost is not in the sense of what we have been saying before about almost everywhere. It converges almost uniformly to a real valued measurable function f if for every epsilon positive there exists a f contained in X, measure of f less than epsilon, and Fn converges to f uniformly on F complement. So what does Egorov's theorem say? That if you have a finite measure space, convergence almost everywhere is the same as convergence almost uniformly. Okay. So converse of Egorov's theorem is true in any measure space. So if you have almost uniform convergence, then you have convergence almost everywhere. Okay, so excess mu measure space Fn sequence of real valued measurable functions, Fn converges to f real valued measurable function almost uniformly implies Fn converges to f almost everywhere. Proof. So let m be a arbitrary positive integer. You choose Fm in S such that mu of Fm is less than any number you like, 1 by m, and Fn converges to f uniformly on Fm complement. So now you set f equals intersection Fm, m equals 1 to infinity, then mu of f is 0 because it's less than mu of fm less than 1 by m, so mu of f is less than 1 by m for each m, so mu of f has to be 0, and f complement equals union m equals 1 to infinity Fm complement. And in any of these sets, so if X belongs to F complement, it belongs to Fm complement, and this implies that Fnx converges to f of x. that is Fn goes to F almost everywhere. So whenever you have a notion of convergence, you also have an associated notion of Cauchy, and then usually convergence will always implies Cauchy, and one is always interested in knowing whether Cauchy implies convergence. That is like important thing which we had with the completeness of the reals and the complex numbers, namely every Cauchy sequence has a limit. So the same idea we will always see whenever we introduce a notion of convergence, we will have an associated notion of Cauchiness, and then convergence should imply Cauchy and Cauchy should imply convergence. Okay, so definition: XS mu measure space, Fn a sequence of real valued measurable functions. So we say Fn is almost uniformly Cauchy if for every epsilon positive there exists an F in S, mu F less than epsilon, and Fn is uniformly Cauchy on F complex. So clearly if Fn converges almost uniformly, okay, then there exists an F such that mu F is less than epsilon, and Fn converges to F uniformly on F complement. Okay, this implies Fn, since it converges uniformly, it is uniformly Cauchy, so uniformly Cauchy on F complement. So convergence almost uniformly implies Cauchy almost uniform. So we want to know about the converse. Suppose you have a sequence which is Cauchy almost uniformly, is it going to be convergent almost uniformly? Okay. So proposition: XS mu measure space Fn almost uniformly Cauchy sequence of real valued measurable functions. Then there exists F real valued measurable function on X such that Fn goes to F almost uniformly. Proof. So again, let M belong to N, positive integer. There exists Fm in S, mu of Fm less than 1 by M, and Fn uniformly Cauchy on Fm complement. So you set F equals intersection Fm then mu f is 0. And f complement is union fm complement. So for every x in f complement, it belongs to some fm complement, and then on fm complement, what do you know? It's uniformly Cauchy. So fn x is a Cauchy sequence. So you define f of x equals limit n tending to infinity fn x if x belongs to f complement, because it's a Cauchy sequence, it is convergent, okay, and 0 if x belongs to f. Now you define Gn to be equal to chi of f complement into fn. So it's a product of measurable functions, so Gn is measurable. And if x belongs to f, you have Gn equals x equals f of x equal to 0. If x belongs to f, f of x is 0. Gn is also 0 because chi of f complement is 0. So Gn equal to 0. And if x belongs to f complement, Gnx equals fnx, which converges to f of x. So this implies that Gn converges to f everywhere, and that implies that f is measurable. Now if fn converges to f on f complement, okay, and what is f complement? F complement is union of fm complement, and therefore it belongs to some, implies, so if x belongs to f complement, then there exists an M such that x belongs to fm complement, okay, and mu of fm is less than 1 by m, and you have that fx, fn goes to f uniformly on fm complement. So given any eta, you can choose m large enough such that it is less than 1 by m is less than eta, and then therefore you will have that this belongs to, it converges uniformly on this set. Therefore this implies that fn converges to f almost uniformly. Okay, so this completes about almost uniform convergence and almost uniform Cauchiness. Next time we will take up another notion of convergence and examine its properties.